Okay, in this video, we will be talking about estimating delta H of a reaction using bond energies. So we just learned about what bond energies were in the last video. If you need to, go ahead and go back and review that. And again, I will give you any bond energies. You can look them up in your textbook. And I know they're given on the homework, okay? So let's just say we have this reaction. This reaction is pretty simple. 2H2 gas plus O2 gas gives us 2H2O liquid. Oops, not liquid. This has to be gas for this to work. Okay? 2H2 gas plus 2O2 gas gives us H2O liquid. And we want to know what the delta H of this reaction is. We want to know basically how much energy is released or absorbed during this process. Well, we can use bond energies to estimate that, okay? And notice I said estimate. So we're going to estimate this. This will not give us an exact energy because, like we talked about in the last video, all these bond energies are averages. They're not specific to any given molecule. Okay, but what we need to do in order to know what bond energies we need to use, we need to know what the bonds are. So let's just look here. What's the Lewis structure for hydrogen? That's it. And how many of them are there? There are 2, okay? What about for O2? Well, O2, if you do the Lewis structure, and you have to do the Lewis structure from scratch, count up the electrons. Of course, there's no central atom. Put single bonds in, you'll find that you need a double bond in order to get full octets. So we have an oxygen-oxygen double bond here. And then if we go to the far side of the reaction, Lewis structure for water. And let me say one thing. Every semester, somebody does the Lewis structure, actually several people usually, for water as this. Please don't let that be you, okay? It's H2O, not HO2, so don't do that. I'm just going to erase that. I don't even want to look at it. Okay, and there are 2 waters. So we do the Lewis structure twice, so we can see exactly how many bonds are breaking and how many bonds are formed. So what's going to happen here when this reaction occurs is these bonds, oh my goodness, I really hope you guys are not super annoyed with me and just cracking up. Feel free to laugh at me. I won't even know. These bonds are broken. And that means on the other side, those bonds are formed. That means they have opposite signs in terms of energy. And if we want to figure out what the total energy of this reaction is, all we need to do is sum up all of the energies associated with the 2 hydrogen bonds, the 2 hydrogen-hydrogen bonds, the oxygen-oxygen-oxygen double bond, and the 4 hydrogen-oxygen bonds. Okay, so what that's going to look like is that delta H is equal to the sum of the bond energies for the broken bonds and those are always going to be the reactants, minus the sum of the energies for the formed bonds. And those are always going to be the products. And that minus sign right there, that minus sign is because the energies are opposite. Okay. When we break a bond, we have to put energy in and that's a positive. When we form bonds, the energy is released, and that gives us a negative. So, in order to complete this, what I'm going to do is just sum up all of those energies. So we had two hydrogen-hydrogen bonds, so it's 2 times the bond energy for hydrogen-hydrogen plus the bond energy for oxygen-oxygen double bond. And let me say this right now, an oxygen-oxygen double bond is not the same as 2 oxygen-oxygen single bonds. So a double bond is not just twice what a single bond is. Minus 4 times the bond energy for an oxygen-hydrogen. It might be listed as hydrogen-oxygen. It doesn't matter which way it goes. Okay? It's the same bond. So I just went ahead and looked all these up, and you'll be able to do that on the exam or on your homework. So it's 2, and really that 2 is 2 moles. And it's 2 moles times 436 kilojoules per mole plus 1 mole times 498 kilojoules per mole minus 4 moles times 464 kilojoules per mole. Okay, and when we do the math on that, what we come out with is negative 486 kilojoules. So if we stop and think about that, we got a negative sign. That means it's an exothermic process. If you've ever seen hydrogen and oxygen react together, it is definitely an exothermic reaction. It's a big fireball. You can just Google it, a video of it. So that makes sense that we're getting energy back out. And then I went ahead and looked up the actual value. Actual measured value, and it is negative 483.6 kilojoules. So does our value that we calculated, and remember this is an estimate, is it pretty good? Yeah, it's a pretty good estimate. It's only off by 3 kilojoules out of 400. That's less than a 1% error, so that's a pretty good estimate.